Can you see my screen?
Yes.
Okay. So my presentation is on the deep learning and cybersecurity. Deep learning is a major type of machine learning and artificial intelligence that is used in smart cybersecurity systems today to provide additional, more effective security measures that conventional means like firewalls and antiviruses and encryptions are ineffective. If it is a broad field that consists of several techniques such as multi-layer perceptrons, recurrent neural networks or RNNs, convolutional neural networks or CNN, autoencoders, deep transfer learning, long short-term memory, self-organizing maps, and deep reinforcement learning. They can offer a variety of security functions like detecting, predicting cyber attacks, fraud detection, intrusion detections, and detecting malware, ransomware, or botnets. So here's an outline of what I'll be discussing today. I'll be focusing on deep transfer learning, the learning process involved with deep transfer learning, its uses in cybersecurity, and the ConvNet TL and SSTL. I'll discuss what those are later. So deep transfer learning is a method used primarily for solving problems with having inadequate training data by training neural networks with small amounts of data and eliminating requirements for training in AI models. Deep transfer learning is often used in real world, they're used in real world applications where data is needed to train AI models when there is not enough data available to train an AI model. They're often used in computer visions, image classifications, speech recognitions, smell filtering, and natural language processing. It uses knowledge acquired for prior tasks to solve related tasks. There are several types of transfer learning types. The inductive transfer learning, which is a situation where a source task and a target task, the new task, differs from one another, but the targeted domain is the same. There's transductive transfer learning process in which the source or target task are similar or the same or similar, while the source and target domains are different. And then there's the supervised training where the target task and the source task are different, but related to each other. So here's a layout or a map of how the learning process works. It uses pre-trained models learn from previous source domains and uses those models to complete tasks for the current task or domain. So it, from a previous source domain or a previous task that it has learned from data from a previous task, it learns it from there and acquires a new knowledge. And then it uses the same knowledge to do a new task or like the target domain to accomplish a new task. So in cybersecurity, deep transfer learning is useful as it takes less time than it would to train and improve the accuracy of output, and it improves the accuracy of output. It works well with less data when there's less training data available. So I'll be discussing two different models. One is going to be on network intrusion detection, and another model is on semi-supervised transfer learning for detecting malware in clouds. Before I go into that, I'm going to discuss what CNN is. So CNN, or convolutional neural networks, is a deep learning network architecture that is able to learn directly from data without feature extraction or pull data from for example, a program for analyzing. They work well without human supervision and are often used in a variety of systems or techniques such as video and image processing or analysis, image classifications, image segmentations, natural language processing, and they have various uses in cybersecurity. In cybersecurity, they can be used to stop DOS attacks, for denial of service attacks, detecting malware, securing Internet of Things networks. They could be used for network intrusion detections to detect and capture attacks by using specific like learning algorithms to detect attacks with limited learning and training data sets. So the ConvNet TL is a system developed that uses two separate CNNs. It uses two concatenated CNNs where one holds basic knowledge of a network intrusion attacks and the other has knowledge specific for a targeted attack model. The CNN model was trained, this CNN model was trained using basic neural intrusion knowledge, and the model was trained using two learning stages. Here's a model setup for the ConvNet TL model structure. It has so it has two concatenated CNNs, CoVNet B and the CoVNet T, where the outer layer is connected. Each layer within the ConvNets have separate layers within them that handles various tasks. Like within this model, there might be two separate layers: the convolution and the pooling phases, where convolution intercepts the packets and the pooling selects the data to acquire from that that it received for further processing. It may also have like a dropout layer for randomly removing connections to avoid overfitting. Here's the training process set up for the model for training. Data pre-processing stage. In the first stage, it trains the ConvNet B by using the basic knowledge of the network intrusion. Afterwards, it
Brandon,
asked, yes.
Can you please let Danny join class? You are the host now.
Oh, I don't know how to do that. Where do I do that?
Just accept the admission. That's it.
I don't see that.
Oh, you've got to go to Zoom.
Yes.
You got to go back to Zoom, and they should be on the top.
Okay. Okay, I can do it. So I'll let you be the host again.
Okay.
Okay. Yes, you can continue now.
Okay. So in the first stage of the CoVNet B, the basic knowledge uses the basic knowledge of the network intrusions for training. Then it asks the CoVNet T, and then it creates the ConvNet TL to create the ConvNet TL stage. And here it trains the newer layers to for the target data set. Then it handles the data pre-processing stages where the missing values are, any missing values that are found are patched, encoded, standardized, and reshaped into a recognizable format so it can handle the data later. So the results for the CoVNet TL was that it was far more effective in detecting known attacks. It could identify new attacks easily, had improved accuracy, but it also had a high false alert alarm. There's another deep learning technique for detecting malware in clouds, where so problems with detecting malware in clouds includes that with using machine techniques is that there are privacy concerns where you had most software requires access to files that tenants would not want because they may have sensitive files or on their clouds that they don't want anyone to have access to. And it could also lead to a lot of false alarms and accidental deletion of legitimate files if if it detects false alarms. There's also a lack of sampling that is required for learning, so it makes it really difficult to train software to detect malware within clouds. So the process for handling that, the semi-supervised training learning model was developed to detect malware more easily while improving the privacy protections for clouds by using innovative malware classifiers. It uses a byte classifier to extract byte features from software, and it uses RNN to classify the order to classify data in order to avoid violating tenants' privacies. It uses the assimilator classifiers to for more accuracy than the byte classifier to predict it creates a new training data set based on it. Then it uses a statistical test to compare and analyze the advantages and disadvantages of the features, extractions, and classification algorithms to make the byte classifiers and the assembly classifiers. So the classifiers design phase consists of 3 phases as an analysis mode, the feature extraction phase, and the classification algorithm. So the analysis mode uses static analysis to extract features from the software without running as actual software. And it uses disassembly tools and dynamic analysis. And it also uses a dynamic analysis to run the potential software in a sandbox-like environment for extracting features. This is important for a certain malware where malware will not run if it detects that it's within a sandbox environment. So it's important to use both phases or both dynamic and static analysis for this. In the feature extraction phase, the bytes for the extracted features and the assembly features are analyzed. And then the classification algorithm phase is where deep learning algorithms are used to identify patterns within the images that it acquires from the bytes or the assembly features to identify rather malware or to train the software to identify the malware. Algorithms are vulnerable to overfitting, however, and some learning algorithms will have a longer training time, and it could require huge computational resources. So this method, the semi-supervised transfer learning model, can identify malware by using static analysis, and it has 3 components. It has the detection component where it detects the binary content of the potential malware header file. That way it doesn't extract any private information from the file. And it sends this to the byte classifier to discern whether it is related to any potential malware families. Then it uses the prediction component where it's used to train the assembly classifier to train it to features for publicly known to train it towards it's trained using publicly known malware assembly features so it can help detect potential malware and unlabeled malware samples. And then it has a transfer component that extracts the bytes and assembly features simultaneously. It uses prediction components to predict the assembly features, and it uses the combination of unlabeled data acquired by the byte classifiers, and it is used to predict labels and transfer samples from the byte classifier and can be learned from data and improve the detection accuracy. So basically, It extracts data from a tenant's virtual machine without invading the tenant's privacy. It extracts assembly features so that it's more for more reliable detection rates and to minimize false positives. Both the byte and assembly features are extracted from unknown and or unlabeled data simultaneously, where the assembly classifier can predict the class and the potential malware family that exists if there are any. Then the byte features and the assemblies are combined and used to train the byte classifiers, which ultimately improves the malware detection rate accuracy. The adaptive assembly machine learning model also has a voting algorithm to help it to avoid adversary attacks. There's a potential attack that hackers have learned where they could try to make the class, if they figure out that it's using these classifiers, they can try to trick them into making mistakes or learn things incorrectly. So the semi-supervised training transfer model had the byte classifier had an accuracy of 94.72%, while the assembly classifier had a prediction rate of 99.6%. And with the transfer component included, it improves the byte classifier from 94 to 96.9%. The assembly model can avoid invading on tenant's privacy, and it functions well with minimum training samples. So in conclusion, deep learning neural networks are effective at minimizing high efficiency, maintaining high efficiency with limited data sets, saving time with training the software, and without the need for training a neural network from the very beginning. They're effective at detecting attacks and securing systems where conventional means fail. Here's some references that I use for the presentation. And that's the end of my presentation. Are there any questions?